everyone. Today we are going to discuss about the demineralization process. That means softening of hard water. So in this process, especially we are going to discuss about the external conditioning, that is ion exchange process, because it is a very efficient method to reduce the hardness from boiler feed water. Usually boiler feed water may consist the hardness producing salts like calcium chloride, calcium sulfate, then magnesium chlorides, magnesium sulfates, and other iron salts also. So these salts may cause harmful effects, that means troubles to the boiler. So we have to remove these kind of hardness producing salts from boiler feed water. So that's why we are giving much importance for this process in water technology, because these dissolved salts may cause serious problems to boiler, as well as it reduces the boiler efficiency also. There are many methods available, but this is an efficient method. Okay, let's see the process which is involving in this ion exchange process. In this ion exchange process, we are using two ion exchanging resins. So these are the main components are present in the ion exchanger. So they are cationic exchanger and anionic exchangers. These cationic and then anionic exchangers are having nothing. They are simply having the resins which are having the respective functional groups to remove the cations and anions which are present in the boiler feed water. Okay, that the anionic and then cationic functional groups which are involving in this process is given in the slide. You can see the cationic resins are having acidic functional groups which are given in the slide, like COOH, it's an organic acidic group, and then SO3H, that is the mineral acidic group. So these groups are present in the cationic exchanger, as well as in the anionic exchangers. They are having basic functional groups, that means alkali functional groups. They are NH2 or amine nature groups, and also the OH minus, that means hydroxyl ion groups. They are having the capability to exchanging the negative ions like chlorides and then sulfates present in the boiler feed water. So now we can clearly understand what is the mechanism involved in the ion exchange process. So this is the structure for cationic exchange resin. This cationic exchange resin is for sulfonic acid. You can see that SO3H group present in that cationic resin, and then the anionic resins are having OH group or other nitrogen functional groups. So this is an example for anionic exchanging resins. They are usually cross-linked molecules. It's not a simple molecule. That's why its structure is little bit complicated. Okay. And this is what the block diagram of the complete ion exchanger. It has two cylinders. So one is for anion removal and another one is cations removal. In that first one, the first cylinder, it consisting the cation exchanging resin. So it is provided with acid regenerator, and then the second one is anionic exchanger, which is consisting anion exchanging resin. It is provided with alkaline regenerator. So first we will see the exchanging mechanism. In that first cylinder, the raw water, that means raw boiler feed water, is fed into the cation exchanging column. So in that the resins which are having positive ions simply exchange their ions with metal cations like calcium and magnesium ions. So after removal of these two calcium and magnesium ions, the cation free water is allowed to the anionic exchanger. So we all know the anionic exchanger is having anion exchanging resin, which is having the functional group OH minus as well as the nitrogen groups. So when the cation free water is entered into the anionic exchanging column, the anions which are present in the boiler feed water, example chlorine and sulfate ions, will be exchanged by the OH minus ions present in the resin. So after this, all the cations and anions will be removed. So the water which is come from the anionic exchanger is completely demineralized water. That means it does not consist any other cations and anions except H plus and then OH minus. That means purely H2O consisting water. It's a demineralized water. Now at this point, I just want to say one thing. In other methods like reverse osmosis and other softening methods, we will get simply the softened water. We have the difference between the softened water and then demineralized water. That softened water may consisting very trace amount of hardness producing salts itself. But in the case of demineralized water, we cannot have any other cations and anions. That means any salt in that demineralized water. That means all the salt waters are not demineralized water. Okay. And then there are two provisions now in these two columns, in cationic exchanging column and then anion exchanging column. So in that cationic exchanging column, one provision is given for acid regeneration. Actually in that column, acid diluted acid is present in that acid regenerator. So once the cation ions are exhausted, this diluted acid will reverse the reaction. So by reversing the reaction, we can again get the cationic exchanger as an efficient one. As well as in this anionic exchanger, there is an alkali regenerator. So this alkali regenerator will provide the anions to the anionic exchanger. Again this process will start with this reverse process. So that the mechanism is given here. So in that reactions, the RH plus Ca plus, so these will be replaced as R2Ca. For the compensation we have mentioned here R2, and then magnesium also, because these two elements are majorly causing hardness to the boiler feed water. That is an example for cationic exchanging reaction. And then in the second one, that is given as a red one now, in that OH minus functional groups are representing the anionic resins. So they are simply exchanging the sulfate ions and then chloride ions. So after these two process completion, that means removal of cations and then anions, at the end of the process we will get the pure water. That means it consisting only H plus ion and then OH minus ion. It's a very efficient method. Even though it is a efficient method, it has some drawbacks also. Before that, just to go through that reverse process, that means regeneration of cationic exchangers and then anionic exchangers. So simply we are reversing that exchanging process. So that product Ca, R2Ca is the product of exchanging process. While we are adding diluted acid, either it is HCl or sulfuric acid, it will reverse, that means it will regenerate the cationic resin and then left the free calcium wastes. Okay, so these waste waters also removed. There is a provision in that column now. So in this bottom of the column, so waste liquor, that is mentioned as waste liquor. So through this provision, this waste calcium and then other magnesium water, that means slags can be removed. As it is in the cationic regeneration, the anionic regeneration takes place. That means the anionic resins will be reproduced by adding diluted alkali. Here that sodium hydroxide is given. You may take any alkali. So it is the efficient method. If you are considering that advantage, it's an efficient method, but its capital cost is very high when compared to reverse osmosis and other softening methods. And then it need keen observation, so we have to give more attention. That means we need a manual support. As well as one more thing, we cannot treat the turbid water by this method. This is what the main advantage of this demineralization process. Thank you. Now we all can easily understand what is the mechanism, and then what is the chemicals, and then chemical reactions are involved in this ion exchange process, why it is an efficient method. All those things we can clearly understand by this. Thank you all. Thank you.